So this lecture for the U54 Research Design and Analysis course seminar series is going to be on some design and statistical considerations you have to make when developing or using patient-reported outcome measures. And my goal here is really just to illustrate a few common pitfalls when you're either developing a PRO or analyzing data that where PROs are a variable in, say, a regression model or something like that. I'm going to focus on latent PROs, and what that means is that they're not variables that we directly observe or measure. Like we can measure somebody's height, weight, those we can directly measure. But these are rather estimated from a number of observable variables that we call manifest variables. So some examples of latent PROs are depression, quality of life, and one that we've developed here at Dana-Farber, knowledge of multi-gene panel testing for cancer risk. And so for each of these, we have a number of questions, 5, 6, up to 30 questions, so even more, to estimate a patient's level on a single variable, or sometimes a few variables related to depression or quality of life or something like that. So the pitfalls I'm going to cover are, there's 3 of them. They're related to sample size, evaluating fit of a measurement model, whether it's a confirmatory factor analysis or a type of item response theory model. And the last one having to do with how do you include a latent variable in a secondary analysis or an analysis to answer a health question or some other question for that matter. And I picked these, there's many potential pitfalls, but these are the 3 that I see the most in particular when I review papers for journals. You really want to avoid them if you can. So I want to also note that there's usually more than one reasonable approach to use to develop a PRO, to include them in the analysis. I'm going to show you the ones that I tend to favor, but there might be other ones that are just as reasonable to use in different circumstances. And which approaches you use are most that are most useful can depend on a number of factors. Who's going to use the scale? How is the scale going to be used, and who's going to implement it? Is it going to be used for clinical practice? Is a clinician going to use it on a patient to measure something for like a screening tool or something like that? Is it going to be used for research? And related to those two, what level of error can you accept? How precisely do you need to measure these constructs? So for sample size, there's 2 pitfalls, really. One is that you have a sample size that is too small, which may lead to a biased or a estimate of, say, a factor loading or the IRT version of a factor loading, which is a discrimination parameter, or you can estimate it without bias, but it has such poor precision that it's not that useful anyway. On the other hand, you might think, oh, I want to make sure that I get unbiased estimates and I have really, really good precision. So you you put a lot of your budget into your sample size, but you might end up with a sample size that is larger than what's necessary. And that in turn uses resources that may be better allocated elsewhere. And this is particularly important if you're doing this for, say, a community group that has very few resources, or if you have a grant with limited funding. You want to make sure you sort of have a good allocation of your funds to your sample size without overusing it. So what is the minimum sample size that gives you useful information is really what you want to strive for. And what's useful here is really dependent on how the scale is going to be used, as well as what parameters of the measurement model you care most about. So if you have, say, a two-factor confirmatory factor model, and you might care about the correlation among the factors more so than the individual factor loadings for some reason. And so you might need a larger sample size to make sure you have unbiased estimate of those. But in general, you want to get unbiased estimates. That should go without saying. That have enough precision so that you can make meaningful conclusions from the data. So there are some common guidelines, and you still see these, or I've at least seen these in textbooks that are still in use today. And some of those guidelines say you need 5 people per variable in your model. So if you have 10 variables in your factor analysis model, then you need at least 50 people, or 10 people per variable, 20 people per variable, etc. You can quickly end up with following these guidelines with a fairly large sample size. So if you have 60 candidate items that you're evaluating, which is not uncommon, and you use the 20 per item rule, then all of a sudden you're required to have 1,200 people or more. And that might be necessary for a lot of uses, but in reality, there's a lot of studies that don't have either access to that large of a population or large of a sample from a population, or can't afford to collect data from 1,200 people once they factor in that they need to pay incentives, pay for postage or programming of a survey instrument, things like that. So if you're able to make do with less than 1,200 people, you'd want to know that. So instead of using common guidelines, I find that simulating data is very flexible and very informative to sort of arrive at a meaningful, arrive at a sample size that definitely isn't too small, but also isn't too large. So I'm going to show you a little bit of R codes just to demonstrate how I use a simulation to sort of arrive at a sample size. And this is a very simplistic example, but nevertheless, hopefully it's illustrative of the general point. So I'm going to create an object here in R called discrim params, which is my discrimination parameters for 5 variables. They're all going to be set equal to 1. So the population discrimination parameters for all 5 variables is 1. And down here, I've just created some intercepts, which we're not going to worry about for now. And then just to illustrate, I've drawn one simulated data set of 100 people. And then I fit a graded response model, which is an item response theory model for ordinal data. And then I compared the two. So you can see the true estimate for each of them are 1. And you can see there's some significant deviation in the sample derived estimate. But we don't have to worry about that for one single simulated data set. What we care about is over the long haul, if we do this 1,000 times or something like that, do we get an average value across all those 1,000 samples that's equal to the true? So I've done that here for 2 conditions, a sample size of 100 and a sample size of 250. So the 2 columns to the left here, the MSEs, stands for mean squared error, which is kind of a summary measure of the amount of bias as well as variance. Is actually the square of the bias plus the variance. should equal the mean square error. So that's the first thing that I typically look at, because if that is really, really large, then I'm not going to have parameter estimates that I find to be very useful and reliable, because one of two things are happening, or one of three things are happening. Either I have an unbiased estimate that has really large variance, or I have sufficiently small variance, but really, really biased estimate. Or both of those can be true, that I have large variance and a large bias. But in any of those cases, if this is really large, um, then I already know that I'm not gonna, and I need to increase my sample size. And what's large is kind of a relative thing compared to what it is you're measuring, the consequences of poor precision, etc. So there's not a strong rule for, or cutoff value for that. So you can see for a sample size of 100, these are all between 0.2 and 0.29. And we can split out the bias and the variance here. And you can see the bias is actually a little larger than I'd like to see it. So because the population value are 1 for all of these, we can interpret those as percent bias. So this from 5.5 to 10% bias with a sample size of 100. And the variance is also quite large. So if we compare that to 250, you can see the mean square error is much, much smaller. So the question then is, do we have really precise estimates that are biased, or do we have unbiased estimates that still have pretty good precision? And so if you look over here, this one variable item number 1 has about 4.5% bias. So that's a little larger than I'd like to see. But overall, I'd say the bias here is fairly negligible and the precision is really, really good. So there's one, I've done this whole simulation study really to point out one thing, which is the sample size of 100 condition correspond to 20 people per item. So if you use the common guidelines of using 5 people per item, or 20 people per item, or whatever in between there you'd want to use, you might end up with bias estimates and poor precision, because that would be even smaller than 100. So you definitely don't want to do that. Here I'd probably redo my, if I couldn't afford 250, where I think that money might be allocated differently to something better, then I would redo this simulation with, say, n equal to 200 and see how the results came out and see if that was sufficient for my purposes. So you can see by varying some conditions, in this case the sample size, you can get a good sense of what's happening in terms of bias and variance. And so simulating data is, I put easy in parentheses here because it does require you to learn a bit of coding. But once you get a hang of the coding, it becomes fairly easy. And it's very flexible. You can vary the values of the discrimination parameters, the number of dimension, whether it's a 1-factor model or 2-factor model or a bifactor model or something like that. The number of items, I used 5, but you could use 5, 10, 15, 20 and compare what happens there. If you have more than one factor, you can vary the correlation among dimensions, whether they're completely uncorrelated or if they have a high correlation, and see the impact of that on your needed sample size. Or if you want to inspect the consequence of misspecifying your model. So maybe the true population model has 2-factor, but can you capture the most of the information with 1-factor, and what's the consequence of that? So you can do a lot with just simulating data. And you want to use what you know from similar scales, your clinical judgment of yourself or your collaborators, to what's reasonable assumptions to make, what are some different parameters, what are some different things we can vary, to see what happens and make decisions from there. The second sort of area where I see a common pitfall is where you're fitting or you fit a measurement model with whether that's a factor analysis or some sort of an item response theory model. All of my examples will be an IRT model, but the general point holds for a factor analysis, a confirmatory factor analysis model as well. So after you fit a model, you want to evaluate whether that model adequately captures your proposed measurement structure. So for example, if you fit a unidimensional model, does that model fit the data well? Or is there, for example, evidence of another factor or more than one dimension in the data? Is there evidence of misspecification? Is there, residual correlation of two manifest variables? I'm not going to go over how to assess all those individual types of misspecifications or misfit that might be apparent, because I'm going to focus on the pitfall that I see with what the global fit statistics are, or what's sort of is an overall summary measure of fit and across the data. And there are some common global fit statistics that are from structural equation modeling, and confirmatory factor analysis is one type of SEM model. One is just the model chi-square statistics, or G2. That's a likelihood ratio statistic. There's also a Pearson version of this. That compares your fitted model to a saturated model. And so if you fail to reject a null hypothesis that they're equal, then you're suggesting that the fitted model is equal to a saturated model, and that would be a good thing. So that indicates good fit. You also have comparative fit index. There's a few similar ones by different names, but this is one of the more popular ones. That compares your fitted model to a null model, or where all pairwise correlations are equal to 0. So you're assuming, the null model assumes there's no relationships among the individual variables. So that should be a very poor fitting factor model or measurement model. There's the standardized root mean square residual that compares your model implied correlation matrix to your sample correlation matrix. And then lastly, there's the root mean square error of approximation, or the RMSA, as some people call it. And that's an absolute fit index that's based on the non-centrality parameter. So I'm not going to go over all of them in detail. I've actually done that in a previous seminar lecture where I talked about structural equation modeling. But I wanted to redefine them here for those of you who haven't seen that one. So to evaluate whether your model has good fit, there's psychometricians have developed some cutoff values for each of these statistics, where they suggest that if all of these are true, or some combination of these are true, then you have a good fitting model. And these cutoff criteria I have here are from an article by Hugh and Bentler. I think this might be the first one to propose or systematically evaluate these different ones, as well as a whole bunch of other ones. And so a lot of more recent research by psychometricians have either revised these or come up with new cutoffs, but I'm going to show these ones because they're very commonly used, and regardless of what the cutoff value are, the pitfall I'm going to show you is still holds. So for the model chi-square statistics, you want a non-significant p-value or test statistic at the 5% error level. For the CFI, you want it to be greater than 0.95, the MSR less than 0.08, and the RMSA less than 0.06 by these cutoff recommendation by Hugh and Bentler. So one of the perhaps frustrating things for a lot of psychometric analysts is that you can have good evidence, or you can have evidence of good model fit by some of these criteria, but not others. One example of that is it's actually very common to have a significant model chi-square statistic, but for the other uh, um, fit indices, you have evidence of good fit. And some people say that's okay because the likelihood ratio is so um, strongly determined by sample size. Others disagree with that. Nevertheless, the pitfall that I'm concerned about and that I see quite often is the related to the model chi-square statistics. And I mentioned that's just a likelihood ratio chi-square, and it compares your observed and expected frequencies for each of the possible response patterns or each of the observed response patterns in your data. And I've shown you how it's calculated. It's a fairly simple calculation. ln stands for the natural log. But just as with the chi-square statistic that you might have learned about for, say, a contingency table or a 2x2 table, comparing two categorical variables, it doesn't have accurate type 1 error rate when you have a sparse table. And a sparse table means you have a lot of cells that are have expected frequencies of less than 5 or less than 1 sometimes. And that can very easily happen when you're evaluating or fitting measurement models, because say you have 10 ordinal variables with 5 categories each, which is not an unusual circumstance to have, then you have nearly 9.8 million possible response patterns. So you can imagine if each of the expected values across response patterns should be at least 5, then you would have to have an enormous sample size. So you're very likely to have many small expected cell counts. So again, it's just drawing one simulated data set of 1,000 people to show you where we can get the statistics. So if we just fit the model, like I've done here using the software, and we print the model diagnostics, you can see that the G2 statistic has a very large value and a p-value of 1. So here we would conclude that it fits it's not statistically different from a saturated model. So we might say that's great. We feel like we have a good fitting model. We can also see the RMSA is 0. We don't have the CFI here yet. We could calculate that. But if we were to actually inspect the observed and expected values for each of the response pattern, and I've pulled that out of the model, and I'm showing you just the bottom 6 out of the total number of observed response patterns here. And you can see it's quite sparse. Freak is observed expected values, and these are all 1, and the expected values are all below 1. So you can already see this is a sparse table. If I showed you the top 6, you would see the same type of thing. So we know from statistical theory that the type 1 error rate is not likely to be accurate when we have sparse data like this. And so the G2 might not be appropriate. So the question then is, can we rely on the other fit statistics? And unfortunately, the answer to that is no, because both the RMSA and the CFI and the other statistics that are like the CFI are calculated from the G2 statistic. So what we want to do instead is to use the limited information variant of the G2. And the M2 is one example of that. It's presented in this paper that I have cited down here. And so you fit this limited information variant of the G2 statistic, and then you can calculate the RIMS and CFI from that. So the pitfall here, and I see this, I would say more often than not, is people just take the value from the output they get from the statistical software and present that, and they might feel good about it, they might not feel good about it. Whatever the conclusions are, they may not be aware that, in fact, the G2 statistics or the Pearson version of that chi-square statistic might not be good enough to use. for their particular circumstance. Lastly, I want to show you a pitfall that I've seen less or rather that I still see quite often, and that is, how do you use a latent variable in other analysis? And I'm going to have another example here in a second, but one approach, which is by a lot of people considered the gold standard, I think for good reason, but there are many other approaches that we can use that can gain some of the advantages of an SEM. I'm not going to consider that here because in biomedical research, I don't see that done a lot. Rather, what I typically see is somebody creates a summed score to include in the analysis. So if you have a very simple example, if you have 3 variables, manifest variables that are scored 0, 1, so it's sort of yes/no questions. Somebody who answers yes to all of those might get a score of 3. Somebody who answers yes to 2 of them will get a score of 2, etc. And another approach is that you can estimate the factor scores and include that in your data set as a new variable and use that as a regular variable in your analysis, like a linear regression or a logistic regression or something like that. I see that less often than I see the summed score. So to demonstrate the pitfall, comparing the summed score to the estimated factor scores, I'm going to do a very small and limited simulation study. And the premise here is that you want to use the latent patient-reported outcome as an independent variable, even though we call it an outcome. Latent patient-reported measure, I would call it. For example, a patient's knowledge of genetic screening or genetic screening results. Say we measure that with 6 manifest variables, and we fit a graded response IRT model. We have a binary outcome, which may be something like a choice of treatment, comparing active surveillance versus chemotherapy or some other treatment. And we estimate the association with a logistic regression. So I'm going to do this small simulation under just 2 conditions. One, when all discrimination parameters are equal to 1. That's analogous to all factor loadings being equal. And one where the discrimination parameters are unequal. In this case, I'm just arbitrarily picking 3 of them are going to have a discrimination parameter, which I'm indicated with an A, equal to 0.5, and 3 are going to have the discrimination parameter equal to about 0.2, or equal to 0.2, not about equal to, actually equal to 0.2. And the results, I'm not showing you the code here, but the results of the logistic regression, I'm just showing you the parameter estimate, is in this little table here. So the first row is, you see theta B is the logit coefficient for the estimated factor scores used in the regression. Sum B is the logit coefficient for the logistic regression, where we use just a summed score in as the predictor. And then I have the corresponding odds ratios over here. And then the second row is when all of the discrimination parameters were equal to 1. So they were all equal. It doesn't have to be 1, but they do have to be the same value. 1 was just arbitrary round number. It could have been 2.5. It could have been 1.5, but I just chose 1. So what you see here is that with equal discrimination parameters, the second row here, the sum scores are practically equal to the approach of using the estimated factor scored as a variable. And the odds ratio, of course, are very, very close as well. When with unequal discrimination parameters, in this case, 3 were equal to 0.5 and 3 were equal to 0.2. Again, 0.5 and 2 were just arbitrary. I just made them up. The logit coefficients are quite different. They're, I would say, about 6% bias here. or I'm sorry, 6% attenuation for the sum score relative to the theta score. And the odds ratios are also smaller, of course, 2.3 compared to 2.18. Now, whether that attenuation is clinically meaningful depends on your area, how it's going to be used, what the consequences are of measurement error. So I can't say, oh, that's substantial or that's not substantial. That really depends on your area. But even if it were not clinically meaningful, that still has implications for power and sample size, because now you're detecting a smaller, you're estimating a smaller association, so you might need a larger sample size. And that might increase the cost of the study. Again, this was a very limited set of conditions. I have not considered the uncertainty estimates, which is also affected by scoring. But one of the points that's made in this article that I have cited down here, which you should all look up if you're interested, is a very good description of the consequences of using sum score inappropriately. One of the conclusions they make is essentially, if you're using a sum score of a latent PRR measure when the measurement model has unequal discrimination parameters or factor loadings, is that you're scoring the model based on a different model than what you fit. Because a sum score really only has great utility when, in research settings at least, when all the factor loadings or all the discrimination parameters are equal. But it might be acceptable in some settings. For example, if you clinical use, if you're just going to screen patients to see where they need more education, for example, some error there, it might be perfectly reasonable and okay, because you're identifying people who need the interventions, and their actual unbiased estimate of the latent knowledge might not be as important. But I encourage you to look up this article. It's new, but it's really good, and it covers the different consequences of using sum score when it's inappropriate. I demonstrated just one impact of that. There's also impact on power, type 1 error, model fit evaluation, etc.